Hi, I'm Magnus, and today I'm going to talk about methane hydrates, cold seeps, and why methane matters for the climate. This isn't ice, it's a methane hydrate, so it can burn when exposed to the air. Methane is a greenhouse gas 28 times more potent than CO2. Methane hydrates are ice-like formations of methane and water formed at low temperature and moderate pressure. They can concentrate methane up to 164 times atmospheric gas, and they can be found throughout the continental slopes and rises of Earth's oceans, and in seas and lakes underlain by permafrost. Small changes in sea temperature have the potential to liberate a lot of methane, which is concerning because methane hydrates may store 1,800 gigatons of carbon globally. That's almost as much as total human emissions ever. Methane hydrates are often associated with features known as cold seeps. Unlike hydrothermal vents, which occur at the edges of tectonic plates and spew superheated fluids, cold seeps form within plates where cracks and fissures in the ocean floor leak methane-rich fluids and gases at seawater temperatures, hence cold. Cold seeps can form all along continental margins, above faults and salt deposits, or where canyons cut into sediments which trap fluid and gas. Some cold seeps develop where warm ocean water causes gas hydrates to release methane. Like hydrothermal vents, cold seeps are hotspots for biodiversity, hosting unique microbial communities and ecosystems which rely on chemosynthesis instead of photosynthesis. These ecosystems offer a window into the interconnectedness of life and geology in the deep ocean. Cold seeps can take many forms, including as brine pools where seawater becomes concentrated in salts, forming a dense brine lake on the seafloor. Cold seep bacteria can also form carbonate structures, and seeps in muddy sediment can explode as mud volcanoes. Mud volcanoes and seeps may emit 6 to 13 teragrams per year of methane to the atmosphere. That being said, up to 90% of methane released from ocean sediments never reaches the atmosphere. While diffusing through anoxic sediments, microbes called anaerobic methanotrophs use sulfate to oxidize methane without oxygen. If these microbes are limited by sulfate concentration or methane is released as bubbles of free gas from vents, methane can enter the water column, where aerobic microbes perform methane oxidation using dissolved oxygen. So these biogeochemical processes play a crucial role in regulating methane fluxes from hydrates to the atmosphere. Concern is growing about the effect of modern global warming on the stability of shallow methane hydrates. Looking back at the Paleocene-Eocene thermal maximum, we see a sudden warming of 5 to 8 degrees Celsius. A sudden change from heavier to lighter carbon isotopes in sediment cores indicate a release of methane from cold seeps. This is because microbes prefer to process lighter molecules, something we can observe in modern cold seeps. This suggests that methane hydrates could represent a slow tipping point for Earth's current period of climate change, whereby anthropogenic warming eventually causes methane release, which warms the planet further, leading to a runaway effect with the potential to release vast quantities of a really potent greenhouse gas. Research suggests that a 4-degree warming of seafloor temperatures on a 10,000-year timescale would shrink the zone of methane hydrate stability by 50%. However, with current emissions and warming trajectories, significant amounts of methane would only begin to be liberated in hundreds to thousands of years, and then only in shallow Arctic areas. Understanding these past events and monitoring methane seepage unveils a complex interplay between geology, biology, and climate dynamics, which is really crucial to unpack because, as we've learned, methane hydrates contain vast amounts of methane, an especially potent greenhouse gas, which is often released from cold seeps, yet neutralized by bacteria, forming important ecosystems. It's imperative that we continue to unravel the mysteries of these enigmatic ecosystems to better mitigate the impacts of climate change, because methane matters.